welcome aboard. So it's the continuation of yesterday's session on critical thinking and computational thinking, primarily on computational thinking. Let us do a quick recap from yesterday. I think we started by defining what critical thinking is, and the need for students to develop critical thinking. Why it's extremely important today for students, not just students, teachers. All of us need to develop the ability to think critically. So we focused on that. When we began the session yesterday. Thereon, we moved to computational thinking. We defined computational thinking and we discussed the four integral essential components of computational thinking. And we looked at some number patterns and, we tried identifying, we looked closely into the number patterns, tried to identify the pattern, the underlying pattern and, how the numbers were progressing, given a progression, what was the pattern and what was the rule. We tried to identify that. And we also looked at encoding and, using letters and assigning numbers to letters and how encoding is, used typically. So those are, some of the things that we discussed yesterday. So we will move on to today's topic. I'll share my presentation. So today, let us take a deep dive into computational thinking. So think differently. I think we talk about thinking, critical thinking, thinking out of the box, thinking differently all the time. But how do we develop the ability to think differently is something we will look into today as well. So thinking differently has many components. Some of them we have listed there. It's about identifying patterns, identifying rules, which form the patterns. How are the patterns represented? And some of the coding techniques and codes that we use when it comes to patterns and progressions. And we will build from what we learned yesterday. So that is going to be the section of today's session. So we did a quick recap, just now. So what were the key things we learned yesterday? So we spoke about breaking down a problem into smaller components. That was the first thing we discussed. Once you break down the problem into smaller components, is there a way we can look for a pattern? How do you identify whether the smaller components are forming a pattern? And when you look at a pattern, are we able to identify the rules behind the pattern? Any pattern will follow a particular rule. It could be one rule or it could be more than one rule, and we will see some of it as we go along today. So breaking it down, finding the pattern and writing the rule eventually will help us solving the problem. So these were the things we looked into yesterday. And today's session, what are the things we are going to cover? So the first thing we will look at is, given a pattern, once we identify a pattern, can we look at the same pattern in different ways? Is there only one way to look at a pattern, or are there many ways of looking at a pattern? That is something we will spend some time today discussing. And then the second aspect is, once we identify a pattern and once we come to a conclusion, that is based on our initial interpretation. Now, the challenge is, can we question our first interpretation? When we identify a pattern and come to a conclusion, that is based on our initial thinking and analysis. Now, the important thing is to question our first interpretation, because there are many real world situations where we may form a certain opinion, we may interpret something in a certain manner, but that would not give us the complete picture. It will be only one side of the problem. It would be only one view of how to solve the problem. There are many sides to a complex problem. So how do we question our initial interpretation, and can we come up with more than one interpretation and look for what is the best interpretation? Those are some things we need to develop, and we will discuss some of those things today. And can we represent information differently? And the whole idea of computational thinking is about patterns, representations, coding, and all these aspects. So we will again look at a few simple patterns, just like yesterday. So on your screen, you see a very simple pattern. And when you teach computational thinking to students, the recommended way to do that is we will ask the students to pair up. The students can, typically two students can sit together and come up with the solution for a particular pattern. So in this case, as you closely observe the pattern, you could see how the pattern is evolving. So the first number is 3, second number is 8, third is 15, 24, 35. And I'm sure by now you would have guessed what is how the pattern is progressing and what is the rule behind the pattern, right? It's a very simple rule, right? So the first number, by adding 5 to the first number, you get the second number. And then plus 7 of second number is the third number. So you see that every number which follows the previous number, the increment is by 2. And it is all odd numbers. So the first, addition starts with 5. And thereon it goes to 7, 9, 11, etc. Right? This is the pattern. Now, this is one way to interpret the pattern. Now, is there a way for us to describe this sequence in any other manner? No, the way we have described is plus 5, plus 7, plus 9, plus 11, and then, you've incrementally represented the pattern. But if you observe the pattern very closely, there is another way by which we can represent this pattern. So that's what computational thinking is about. The same pattern, there are many ways to interpret and many ways to represent the same pattern. So take a minute, think through, and identify or come up with another method of representing the pattern. Yeah, I'll just give a pause for 15 seconds and I'll show the other way of interpreting this pattern on the next slide. I'm pretty sure all of you are maths teachers and science teachers. You would have guessed by now. Let's look at how the same pattern we interpret differently. So, okay, this is moving on to another example. Hold on to the previous example. Now let's look at this example. Now each number here is incremented by 2. Now think about how the same pattern can be represented in another manner. Think about it. Yeah, just a few more seconds. I'm going to show the other way of representing the same pattern. Yeah, so as you could see, the first method, it is plus 4, 2 plus 4 is 6, 6 plus 6 is 12, 12 plus 8 is 20. That is one way to represent one way to explain the pattern. Now, the same pattern, how do you represent it differently? That is the second method. So 1 into 2 is 2, 2 into 3 is 6, 3 into 4 is 12. So the third number is 3 into 4. The fourth number is 4 into 5. The fifth number is 5 into 6. The sixth number is 6 into 7. So as you extend it, what will be the seventh number, right? So the seventh number is, as you guessed it right, it is 7 into 8. The eighth number is 8 into 9. So very clearly you could see that, the same pattern the same sequence. On the left hand side, there is one way to represent or derive the rule. The same pattern, we are also able to derive another rule for the same pattern. So the bottom line for us is, any pattern, we need to observe closely and look at different ways of representing the pattern. And it is also likely in mathematics that there could be some patterns where you may not be able to represent it in more than one way. That is also possible. But many patterns, we should not stop with only one way of interpreting it. We should think critically and look at different ways of identifying and representing the pattern. So that is the important message for us, right? Yeah, so from pattern to rule. So this sequence here, this is another sequence. Now, so one way to identify the pattern, identify the sequence, as you could see, it is addition by a factor of 4, 6, 8, 10, 12, 14. It goes on like this. So again, observe closely and, is there another way of representing this pattern, another way of interpreting this pattern? Think for a minute. We will look at, one more way of representing this pattern. Yeah, observe, recognize, generalize, think mentally, write down this pattern on your notebook and take it as a challenge to look at how do you represent it other than what is given here, right? So the first way to represent is +4, +6, +8, +10. And the second rule, the second way to represent is 1 into 2, 2 into 3, 3 into 4, 4 into 5, 5 into 6. So clearly you could see, there are two different ways of representing the same pattern, right? So the rule important takeaway for us is observe a pattern, recognize, how the pattern has evolved, and from the observation and recognizing the pattern, how do we come up with the rule? By generalizing, we come up with the rule that underlies this pattern, right? Moving on. So this is another very simple pattern. Now, the very easy and intuitive, the first answer that comes to our mind is 21. Because as you could see, these are all odd numbers, right? It's a sequence of odd numbers, 1, 3, 5, 7, 19, 21, etc. But the same pattern, if you think differently, instead of 19, we could come up with a different number. After 19, instead of 21, 21 is one answer, which is one of the right answers. We could have another right answer. Maybe there are more right answers, but I know of one right answer which I learned from. This is a very favorite example of Professor Kamakoti of IIT Madras. I remember he repeating this in a few interviews, some of his YouTube interviews. You could see, when he talks about critical thinking, he has given the same example. And it's a very interesting take on this pattern. How do you come up with a slightly different answer, which also, fits nicely to the same pattern with a slightly different kind of a rule? Can anybody type the answer on the chat box or on the Q&A? A different answer to this problem. If you have guessed it by now, go to your Q&A. You can type the answer. Wait for a minute. So go ahead. 21 is the obvious answer. Any other answer you could think of, teachers? Until I got the answer, it was also it was difficult for me as well. It wasn't an easy answer. But the moment we look at the answer, the moment we hear the explanation, we will go like, this is so simple. Why did it not occur to us? It's such a simple answer, but it's not easy to guess. Yeah, so I see one hand going up. Nageshwara Rao, sir, you could type your answer, sir. You you know the answer, the different from 21. What could be another number which follows this sequence? Okay, I'll give the answer now, and I'll also give the explanation as to what the answer is. Yeah, so let us observe the pattern very closely. You see that all the digits in the pattern so far have all been odd numbers, right? Not just the numbers, the digits also. So when you look at the 2-digit numbers in the sequence, they are also comprised of wholly odd numbers. So if you look at 11, it is 1 and 1. If you look at 13, it is 1 and 3, followed by 1 and 5, 1 and 7, 1 and 9. So the other answer that we could think of in the same sequence is, how do you represent a 2-digit number which follows 19, but both digits being odd numbers? So the answer is 31, because you have exhausted from 11, you've gone to 13, 15, 17, and 19. So from 1, what is the next odd number? That is 3. So the first digit becomes 3. And from 9, the second digit will become 1, because it has gone from 1, 3, 5, 7, 9. So again, it will start from 1. So from 19, the next number will be 31. Then it will be 33. Then it is 35, 37, 39. After 39, it will be 51. So this is a very nice little twist on the same sequence, right? If you go by purely odd numbers, it will be 21, 23, 25, which will follow 19. But if you look at both digits being odd, you get 31, 33, 35. So now we know that if you think critically and spot another way of solving this problem, another rule, if we are able to identify, it gives us an entirely different pattern, right? So, numbers have these potentials, right? You can think of n number of ways in which, we can come up with these patterns. So the key was to think differently, and thinking differently, as much as we say this, it's not easy for us to think differently. It requires a lot of practice, and which is why we have to start early when students are in middle grades, and if we train them to think differently, and thinking differently becomes a habit. It's more than a habit. It's a skill that is acquired over several months together. Then it becomes a habit. So thinking differently is the key here. So we were discussing this slide, and we looked at the solution. When we come up with a different view of the same problem, look at the problem slightly differently. When you think differently, you are able to come up with an entirely different solution, right? That was the interesting aspect of this puzzle right here. So looking deeper into computational thinking, thinking differently is the mantra. Now, so what are some of the aspects of computational thinking? Again, observing closely. What are we seeing? when you observe a pattern, take a moment, observe it really close. And from our observation, what could be the rule? Let us identify, observing the pattern, observing a problem. Are we able to come up with a hypothesis? Are we able to come up with what is the underlying rule that defines the problem? That is called hypothesizing. What is the third step? So when we come up with a particular hypothesis, when we kind of decide on a particular approach, and let's say there is a pattern, and we decide that the pattern, the underlying rule is +2. Say 1, 3, 5, 7, 9. If the pattern goes like that, and we have, let's say, based on our initial observation, we come up with the rule that every next number is incremented by 2 from the previous number. Assume that is the rule. Now we need to test that rule with the entire sequence, whether the rule is uniformly applied. When the rule is applied, does the sequence follow the rule entirely? Are you able to justify every following number with the same rule? Or are you able to identify some inconsistencies? So that is the testing process, right? Then the next aspect is, as we saw in the previous example, we were able to come up with one hypothesis, one rule, and that rule worked perfectly well. But when we paused, when we thought about it, when we looked into the pattern again, when we thought differently, we were able to come up with another pattern or another approach to the same sequence. So the same sequence, the same pattern, we were able to come up with, identify another rule, and the pattern took a different turn from the middle of, the first pattern up to 19. It was both the patterns were same. From 19 onwards, if you apply rule 1, the progression was different. It moved from 19 to 20. If you apply the second rule, which we discussed, the pattern, instead of 21, we got 31, then it became 33. So clearly, to a certain limit, up to a certain number in the sequence, both the patterns were same. But after you applied the second rule, from there the pattern diverged. So this can be applied to the same concept we can apply to other real world problems also. There could be a few initial patterns which may be repetitive, but up to a point, two patterns could be same. But after a certain point, the sequence could diverge completely based on a specific rule. That's the important learning for us. So before trusting a pattern, apply all the above 4 steps every time. So important for us to test the pattern, test our rule, and whether the rule works consistently across all the sequence. That is an important element. And questioning the rule is a very, very essential part of the critical computation. So we were able to, demonstrate that in the previous example. Now let's look at some geometric progression. So far we looked at arithmetic progressions, and moving on to geometric progression. All of you are mathematics teachers, so you all know better. You know better in terms of what is geometric progression, because you've been teaching geometric progression for several years. So we don't have to teach you geometric progression, but we will show you some patterns. Yeah, this is a very, very simple geometric pattern, geometric progression. And by now you could have guessed the next number in this progression, and you would have also guessed the rule, underlying rule. Yeah. Yeah, so it's a simple progression where every number is multiplied by 2. And the other interpretation could be, based on the positional value of the number, is there a way you can come up with another rule? Think about can you come up with another rule instead of multiplying by 2, the previous number multiplied by 2? Is there another rule which will explain this pattern? That is something you have to think and note it down. And similarly, on the bottom right, you see a pattern, a progression which is downwards. From 81, it came down to 27, came down to 9. So obviously, you see that it is a division by 3 kind of a progression. Both are geometric progression. One is multiplication, another is division. Now we will also look at some patterns within pattern. One sequence can contain more than one pattern. Is this possible? Yeah. So let's analyze this pattern. What is next? So the first way to interpret this pattern is every number is it is represented by the square of that particular position. So the first number is 1 square, second number is 2 square, fifth number is 5 square, next is 6 square, right? This is one way to represent the pattern. Can you quickly think of the other way to represent the same pattern? Let's look at it. Yeah, so it is 1 plus 3, 4, 4 plus 5 is 9, 9 plus 7 is 16, 16 plus 9 is 21, so 25, 25 plus 11 is 36, 36 plus 13 is 49, so it goes like that. So the same pattern, two different rules, right? The same sequence reveals two structures depending on how you look at it. So as maths teachers, these are the things that you will want to explain to children and make them appreciate the beauty of mathematics and especially these progressions. So the patterns, as we also looked into it briefly yesterday, it need not be just numbers, numeric progression. We can also look at alphabetic progressions which are based on letters. Yeah, so this is a very simple pattern where it is, as you could see, it is followed, the progression, first letter is capital, second is small, third is capital, fourth is small. So it is an alternating pattern of capital and small case, uppercase and lowercase letters. Very simple pattern, right? And so you can clearly guess the sequence. It's a very simple pattern. So now here is another, the next level of the, pattern where we assign numerals, numbers to every letters. This is an example we discussed yesterday also, in encoding, in software engineering, when it comes to data security, similar concepts are used where for every number, they may be assigning alphabets, or for every alphabet, you assign numbers. It can work both ways. So the simple concept here is, assuming you start with 1, assign the number 1 to A, and 2 to B, and 3 to C, and goes on till 26 for Z. So when you say 3, 1, 20, you could easily say it is cat, right? C-A-T. The letter 3 is C. Letter 1 is A, and letter number 20 is T. So 3120 is cat, and the same, extending this, you can come up with n number of patterns, right? So what is 5, 4, 5, 18, 7, 25? So you can clearly guess the pattern, from given the numbers, when you represent it in alphabet. So the numbers, the sequence becomes energy in English. In numbers, it is 5, 4, 5, 18, 7, 25. The equivalent in English, it becomes energy in English alphabets. Yeah, 6, 15, 18, 3, 5. Obviously, you will be able to do that very quickly mentally. So E is 5, so which means F is 6. What is letter 15? It is O. So it is going to be force, right? So very simple, engaging ways in which we can teach these patterns to children, students in middle grades. It's a very nice and very engaging concept, engaging way to teach them the progression. Yeah, you can divide the students into smaller groups, or students can work in pairs, and give them a few English letter words, ask them to come up with the numeric codes, give them a few numerical codes, and ask them to find out the equivalent English words. It's a very fun exercise, but also in the process they are able to learn the arithmetics, as well as the alphabets, and their literacy as well as numeracy is strengthened by such simple exercises. So what did we practice so far? So given a sequence, we were able to spot the structures. We were able to describe the rule clearly and precisely. That was the first thing we were able to do. Second part is given a pattern, were we able to, from the specifics, were we able to come up with a generalized uh, pattern, or a generalized structure that kind of represents the pattern. So from a specific, a small set of numbers from the initial pattern, are you able to come up with the structure for the entire pattern, which will follow the initial set of sequence? Yeah, so the important thing is, once you arrive at a pattern, once you generalize and come up with a pattern, or the rule, initial rule, the key for us is to question the rule, because the first rule that comes to our mind could work for the initial few numbers or a few letters, few positional values in a sequence. It may stop working beyond a certain point. So the critical thing is, once you come up with a rule, the rule has to be consistently working correctly for the entire sequence. So that's an important aspect of these progressions. So questioning our assumption and testing it to make sure that you get the rule right is extremely important. And we also learned that given a set of numbers or a sequence, there are multiple ways in which the same initial sequence can be represented. Up to a certain point, the sequence could be same. Thereon, if you apply rule number 1, the sequence 1 will look differently, and from the same point, if you apply rule 2, the sequence will look entirely differently. So, representing differently, showing the same information in more than one way, that's another thing we learned. The same sequence, even though it can be entirely same, it can be represented in two different ways. That is also something we learned. So the takeaway, if you look at it, is to look deeper, think differently, and what did we notice? What are the rules that explains it? Is there only one rule that defines the pattern? Can we come up with alternate rules? And test, once we come up with a rule, can we test the idea? Can we test the rule? Can the same sequence, can it be represented differently? Can we question our initial assumptions? So the most important thing is, the goal is not to find an answer. It is to understand the steps, that leads us to the answer. As we discussed, there are multiple steps in arriving at different, the same answer, or it could be different answers. So the steps are more important than the answer. So spot, describe, generalize, question, test, represent. These are the important components. These are the important concepts that we learned in computational thinking. So with that, we come to the conclusion of this session. So hope you all followed the session closely, and hope you were able to understand the concepts that we discussed, and how thinking differently can lead to different sequences, or the same sequence being represented differently. That's the beauty of the computational thinking. So I'll pause here, and if there are any questions, Q&A box, we can discuss, or Karthik can give the poll. There is one hand. Narnoor Palan, perhaps you can type your question. Subhashri, Karthik, we can give the poll and close the session. Any questions from participants? Karthik, do you want to administer the poll now? The Q&A? Karthik, you there? Computational thinking, and thank you all so much for your participation today. Thank you so much, and have a fantastic evening. Good evening, good night, all the best. We can close the session, Karthik.